we are the group number 15, and we are going to talk about factors influencing sound pressure in modern wind turbines. So, for the aerospace industry, the noise generated by an aircraft is an issue of environmental and efficiency matter. As rotor gets larger, the tip speed gets quite high, resulting in noisy operations, and this makes a constraint in places where aircraft-related structures can be located because they're not going to be suitable anymore. Noise is going to disrupt the environment, and this represents loss of money. So, thus, noise is a crucial factor in the design of modern airfoils for wind turbines. And this is why NASA is looking for the reduction of the external noise generated by the whole airframe of an aircraft. An important factor of the total airframe has been the airfoil self-noise, which is the total noise produced when an airfoil encounters a smooth, non-turbulent inflow. Or in other words, this is produced by the interaction between an airfoil blade and the turbulence produced in its own boundary layer and near wake. The picture that you're seeing on the right is more or less for you to get an idea of what I'm talking about. So research has been conducted and supported by NASA, and the main question is, can we predict different self-knowing mechanisms in order to test methodologies to create the best model so we can reduce efficiently the noise? And among these methodologies has been the semi-empirical models, and among the semi-empirical models, that is the BPM model, that is called BPM because it was developed by Brooks, Popp, and Marcolini in 1989. And this model is used to predict the self-generated noise of an airfoil blade, encountering a smooth flow as a function of the angle of attack, the free stream velocity, or geometric parameters of the airfoil. Nevertheless, the BPM model does not predict accurately the scale sound pressure level variable, which is Y, pretty much. And so that's why different people have done different works in this, like approaching this question with technologies based on neural networks, like Loud et al. In 2006 or 2008. And these technologies is pretty much a collection of data processing units that they're called neurons. And then they're interconnected to each other, and they get input of information, and then as a result, they process this information, and then they put this information as an output. And after reviewing the prediction quality of all the configuration tested, Loud et al. Showed that the neural network provides actually good results for an independent tested data of SET. So we decided to take this data from the UCI machine learning repository. This data was donated to the repository in 2014, and we found the data as a .dat document or file, and it has no the labels on the file. So what we did is take this data, put it in an Excel file, and then the labels that were seated on the UCI machine learning repository, we placed them manually, and so we can work on R easily. Also, in the UCI machine learning repository, we have seated 3 different papers. We found the papers in different sources, and in the last slide of the presentation, you can see references, the links directing to these 3 different papers. Nevertheless, here we are showing a folder where the 3 papers are together in case you want to check them out. And this, our question becomes, we have 3 different questions, right? One is, which is the parameter that provides the most weight into the prediction accuracy of the noise produced by the NACA 0012 airfoil? The pictures that you see on the right is for you to get an idea what we're talking about. And this is a demo, pretty much. Another question is, does our data set have any biases? And our third question is, if we have violations, can we transform our variables to eliminate them? And this data set, that for now we call it NASA data set, contains 1,503 entries. We use all of them to work with in this project. And in the table that you're seeing, we have on the variable column, we have 6 different variables. 5 of them in blue are the response variables, or excuse me, the explanatory variables, which is the blue, or x-axis in a graph. And we have frequency in hertz, angle of attack in degrees, core length in meters, free stream velocity in meters per second, and suction side displacement thickness in meters. And lastly, we have our Y variable or response variable in green, which is the scaled zone pressure level in decibels. All of these variables are continuous type.
Okay, so thanks, Santiago. So preliminary analysis, looking at the data set, we knew we needed to do some graphical interpretation to kind of get a feel and know where we wanted to go with our project. So we looked at histograms, scatter plot matrices, and also residual plots to kind of see the violations and where we could address it. So first things first, we looked at the histograms. We made a histogram of the frequency, the suction displacement, the chord length, the free stream velocity, the angle, and the sound pressure. From this, we saw that frequency, suction displacement thickness, and also the histogram of the angle all were kind of right skewed. This could be problematic down the line as most of the data set was lower values. But in addition to this, we also saw that our sound pressure level, which is our dependent variable, was normally distributed, which was good for our data set because we had a lot of data points, and that means we have a lot of values for sound pressure to work with. Next, we looked at the scatterplot matrices to see if we could kind of see any linear relationships between all the x values and the y value. From this, we kind of saw that there's no real linear pattern. It seems that there's no SLR relations, which could be problematic down the line. But in addition to this, we also saw that the angle and the suction kind of had a linear pattern, which could lead to multicollinearity. So further analysis was needed to kind of delve into what was going on with our matrix. Then lastly, we looked at the residual plots. From the residual plots, we saw that most of the variables looked like they had constant variance with a straight line. However, frequency had a clear curvature pattern in its graph, and that made us wonder that maybe that and other variables did not actually have constant variance. And this can also be seen in the fitted values, as it also has a downward curvature pattern.
All right, thank you very much, Jeff. So having considered our data set and done a number of preliminary studies on them, we decided to fit the data using a linear model. But then we observed that this linear model actually did not conform with most of the assumptions of normality, constant variance, outliers, and independence, and all of that. So we decided to look at other possibilities of fitting these data sets using another model. Next slide. So we actually looked at the quantile plots. We looked at the Shapiro test to confirm normality, but then we discovered that this data set failed the test of normality, which was something that actually gave us concern. Then we looked at other plots. Next slide. So we looked at the Brown-Forsyth test for equal variance as a test of equal variances, and we observed that for pressure, for frequency, for chord, these variables actually failed the test of equal variances, and it was also something that gave us concern and made us look in other direction. Next slide. So as well, we actually looked at possibilities of having outlying values in variables, and we looked at the inferential points. We discovered that for the Y observations, which is the response variable, there was no outlying observation. However, for the X observation, for the X variable, the explanatory variables, there were a number of outlying observations, and this further gave us concern as to if we're going to continue using this linear model or not. Next slide. So, having checked all assumptions, several transformations of the data sets were done to annul the violations, and we discovered that these violations actually persisted. Having done box cost transformation for our response variable, having employed log transformation, sketch transformation, inverse function transformation for our explanatory variable, we observed that this didn't change so much on our data set, and we actually found it wise to actually redefine our model, and that was what led us to considering a polynomial model for this data set. So, and our polynomial model in this case actually included the second order terms. So looking at this, We know that when we use a polynomial model, it usually comes with a problem of multicollinearity. And to actually solve that problem, to reduce multicollinearity, we decided to weight our data set. And this is what this particular page is showing, where we have two summary tables, one on the left and the other on the right. The one on the left is showing the unweighted polynomial model, and while the one on the right is of the weighted polynomial model. Now, if you look down, you see where we highlighted two values in yellow. The one on the right, on the left, is that of the unweighted polynomial model, where we have an adjusted R-square of 0.5487, which is like our explanatory variable has just about 54.8% explanation of the response variable. This is not something reliable to work with. And looking at the right-hand side, where we have the weighted polynomial model with an adjusted R-square of over about 80%, this is something that gives us more reliability as regards to the data set explaining the response variable. Okay.
Oh, sorry. Thank you. So after we decided to go with the polynomial model, we decided to subject our model to model selection procedure, and a table is shown on the next slide. So from the table, it can be seen that model 7 and 10, which is the full model, seems to be the best of the models to use. But I would like to say that the difference between them is really very small, marginal, but it is still clear that model 7 has the highest R-squared value, highest R-adjusted value. The CP was also the lowest and very small to the parameter value. The AICP was small, the SBC was small, and the press-P value was also small. So, but the question is that, should we go with model 7 or go with the full model? So on the next slide, we also did a partial F-test on our polynomial model to check if the second order terms can be dropped. But the test gave us a significant result and says that we cannot drop our second order terms, and that a first order term will not be sufficient to use in this model. So based on these two results, we decided that we'll stick with our full model because, number one, our data set was drawn from a very controlled experiment. So we have to retain all of our predictors, and also since our F-test says that we can't drop the second order term, so we decided to go with all the terms in the polynomial model. That's it.
Okay, so here's some results that we kind of came to after doing our methods and coming up with some conclusions. So first, again, we decided on our full polynomial model due to the experiment being controlled and it also passing a partial F-test to show that we needed all the variables. So the model looks like pressure, frequency, angle, chord, velocity, suction, frequency squared, angle squared, chord squared, velocity squared, and suction squared. And this was compared to a bunch of other models as we've gone over before, and we saw that it was marginally different, so we decided to go with that model. Then the parameter estimates can be seen in the lower table in the lower left-hand corner. With this, we were able to generate a 90% confidence interval for a 95% confidence interval, pardon me, of the parameter estimates, and able to see kind of where our values would lie when using the prediction model. And lastly, an ANOVA table was generated to look at the variance of the different parameters and kind of judge where our model's error percentages were coming from. So then that was it for our results.
Thank you, Jeff. So talking about the discussion, we can see that, so we had, at the beginning, we had some research questions to answer. So we want to see how well did we answer these questions that we had. So the first question we had was to check that all the parameters we had, was there any one of them that was more weighty in the prediction model? And from that, we saw that all the variables were relevant to the prediction model. There was none of the variables that was dummy or irrelevant, and that all of the variables contributed substantially to the prediction model. So the second research question that we had is that, does our data set have any bias? And we can say that because the experiment is a controlled experiment and that we have a substantial sample size, there was no bias in our experiment. The experiment, the data set was obtained in a random manner. The third question we had was to check if there were violations in the assumption and if you could rectify them. That was when we were using the linear model. And we saw that after trying to transform the data, it was still not able to meet the linear model assumption. So we went for a polynomial model and then we weighted it. So that means that we were able to find a way around the violation, even though after transforming it didn't work. We would use the polynomial model. And looking at it, looking at the polynomial model, we decided to work with, and that the original data set was analyzed with a neural network machine learning algorithm. So we looked at it. The polynomial model we use, what are the advantages that it has and what are the disadvantages it has compared to the machine learning model that was used to analyze data. And we can see that the polynomial regression model that we use is a simpler model compared to the machine learning algorithm, which requires much more expertise and statistical knowledge. And we know that and also see that the polynomial model we had would not lead to the usual overfitting compared to the machine learning, whereby when there is overfitting, small marginal difference in noise pattern might become difficult to differentiate. We also can say that the polynomial model is user-friendly and can be used by anybody, irrespective of their experience. This is different from the machine learning algorithm in the neural network, which requires much more knowledge and much more familiarity with computers and machine learning. Now, we would also look at the polynomial regression model. What are the disadvantages or the cons of the polynomial regression model? Compared to the machine learning algorithm that has just at the high value of 91%, you can see that the accuracy of the polynomial regression model is lesser than the machine learning algorithm, where we have high square of 79. So for our polynomial regression model, we had 79%. And the machine learning in the neural network they used, they had 91%. We also know that for us to use the polynomial regression model, because we standardize, for a new prediction to be made, the new variables will have to be standardized. So anybody cannot just pick the polynomial regression model that we came up with and put it in without standardized. The result then will be false. So that's one thing that might consider to be the disadvantages or the cons of the polynomial regression model compared to the neural network. Now, so let me come to, having talked about what is the general overview of let's now summarize everything about the analysis. Now we can see that the polynomial regression model was the best fitting model for the Airforce noise. We checked, we tried the linear model and it didn't work. So the polynomial model was the best fitting model. And that all parameters are necessary for the prediction. None of the parameters was dummy or redundant. And that all generated prediction will need to be standardized before it can be used. So we cannot just pick a variable for new prediction of the noise pattern, that's a pressure, and just slot it in without standardization. Like I said earlier, the result then will be false. And with this, this is the end of the presentation. And then next we have the references. So these are the list of our references. And with this, I'll say thank you everybody for listening to this presentation. We hope you find it useful. Thank you.